Welcome to our Design Day video. We're Team 21019 Capacitive Volume Sensing. Our sponsor is Daniel O'Connor at Roche Tissue Diagnostics. On our team, we have one industrial engineer, Ollie, one mechanical engineer, Brian, one biomedical engineer, myself, Kaylee, and three electrical engineers, Cooper, Ignacio, and Craig. Throughout our presentation, we're going to be going through this poster, so I'm going to start us off with the introduction. On the upper right-hand corner, you can see the Ventana HE600. This is a machine that automates tissue staining to diagnose diseases such as cancer. It dispenses reagents on top of tissue samples, which are on microscope slides, and it can process approximately 200 slides per hour. The reagents are currently housed in 1-liter reservoirs that contain mechanical digital signal floats, and they measure the liquid level at 2 discrete volumes. The location of the reservoirs can be seen boxed in red in that upper right-hand corner, and the floats can be seen in the lower right-hand corner as the yellow components inside of the reservoirs. Now I will pass it on to Craig for the objectives.
Thank you, Kaylee. So the floats are in direct contact with the reagents, so they break down easily, putting excess strain on the system pumps and creating the need for constant replacements. So Roche was aware of this, and they were looking to replace these floats and instead measure reagent levels using contactless capacitive sensing technology. So the objective of this project is to develop a volume measurement system using a contactless capacitive volume sensor to detect and measure the volume in the reagent reservoir at any given point in time. So the project aims to achieve a simple, low-cost measuring system of the reagent fluids while maintaining a high degree of precision, accuracy, and resolution. To monitor the fluid level in the reservoir, a graphical user interface will be implemented that displays the current volume measurement in the reservoir. Now to talk about the system requirements, I'll pass it on to Brian.
Thank you, Craig. So to the left, you'll see a diagram of our reservoir, which depicts various fluid levels with specific system requirements. The first requirement is that our sensor shall have an accuracy of plus or minus 22 milliliters. Accuracy refers to how close a reading is to its true value. The second requirement is that our sensor shall have a precision of plus or minus 2 milliliters. Precision refers to how close readings are to each other. The third requirement is that our sensor shall have a resolution of 50 milliliters. Resolution refers to the smallest reliable reading our sensor can take. Subsequent requirements include our sensor shall not come into contact with the fluid inside the reservoir. Our sensor shall detect fluid level changes with a range of 14 centimeters vertically. Our sensor shall provide an interface with a GUI that can display real-time information. And our sensor shall have a minimum sampling rate of 50 Hertz. And now I'll pass it on to Ignacio.
Right, so I'll be covering our initial point design as well as our final prototype. Let's start with our initial point design for the flex sensor. The three sensors have the same basic layout. Our first design concept is a non-shielding ratiometric measuring sensor. The middle design adds a shielding layer which limits parasitic capacitance. And our third sensor is an out-of-phase technique which limits parasitic capacitance by taking a differential capacitance reading. And after discussing and analyzing the different sensing options, we decided to do the ratiometric measuring sensor with a shielding layer for our final design. And this is our final prototype. Our computer assembly consists of an FTC 1004 capacitance to digital converter, which measures and sends the capacitance values to our Teensy 3.2 board. Our microcontroller then calculates the corresponding volume and sends them to a computer to have them displayed on our GUI. An aluminum case was also designed to further limit outside noise.
Last fall, we began analyzing and prototyping. We started by selecting the FTC 1004 capacitance to digital converter chip and the Teensy 3.2 microcontroller. We used the FTC 1004 EVM evaluation board to test the functionality of the FTC 1004. This allowed us to test the chip fully with an already integrated system and GUI. We also used the EVM to conduct our research portion of this project. The most important analysis done was to see if the FTC 1004 would be able to meet resolution requirements. On the left is a sketch of how the electrode adhesive sensor is designed, and on the right is the equation of how height is calculated through capacitive sensing. By manipulating this equation, we were able to determine that our chip was capable of meeting the sponsor requirements in an ideal environment. Research was conducted to determine what changes needed to be made to allow our sensor to adapt to a non-ideal environment. 3 variables were manipulated in the research: the size of the reference liquid electrode, the thickness of the reservoir, and a filtering of the data. Since reservoir thickness and filtering can't be manipulated in the HE600, this research was done for the purpose of gaining a better understanding of capacitive volume sensing. Now I will pass it back to Ignacio for the requirement verification and results.
Thank you, Cooper. So now I'll go into the final system requirement verification and results for our project. The size and measurement range requirement for our sensor was met with our final dimensions being 17 by 8.6 centimeters with a vertical measuring range of 14 centimeters. Since we used Roche's reagent reservoir, the reservoir size and pressure rating both passed as well. And this is our implemented GUI, which displays the real-time volume in the reservoir and has an exporting feature to export data to a separate CSV file. Continuing with our requirements, the sampling rate requirement was also passed since our microcontroller and FTC 1004 chip were both programmed to read at 100 Hz. We also had a power supply and operational temperature requirement, which was also passed. The final set of system requirements relate to the measuring performance of our sensor. However, during the building stage of our project, we realized our final prototype was not designed with proper grounding. And when building our sensor, we did not have an ideal lab setting with grounding equipment and ESD mats. We believe that this resulted in our final prototype electronic components failing due to electrostatic discharge. And with no time to order or rebuild our sensor, we were unable to successfully test our final design for these performance requirements. However, significant prototyping was done for our sensor, and as you can see from our results, we are meeting or exceeding the performance requirements for accuracy, precision, and resolution. And now to discuss our deliverables, I'll pass it to Ali.
Thank you, Ignacio. Now I will be quick discussing our customer deliverables, starting with the integrated software hardware prototype, which will be delivered on May 6th. Then we have the final report and a research paper that discusses our final progress and findings about the project, also due on May 6th. And finally, we have the customer satisfaction report, which will be done on May 10th. Now I'll pass it over to Kaylee, who will discuss the lessons we learned throughout the project.
Thanks, Ali. So overall, we were able to verify most of our system requirements, and the ones that we were not able to test, we were on track with our initial prototyping. In addition, we conducted our research that detailed the best resolution that our design could achieve. Our largest roadblock that we encountered during the project was the effects of electrostatic discharge. During prototyping, we didn't have any issues with our grounding. However, once we integrated all the components, we began to encounter some issues. Since our design wasn't properly grounded and we didn't build our prototype in a proper lab setting with electric discharge mats and ground plates, the microcontroller and FTC 1004 chip were subject to electrostatic discharge, which rendered them non-functional. In the future, we would incorporate a grounding scheme into our design to eliminate this issue. We also learned how to adapt to issues outside of our project, such as vendors changing lead times and how to navigate a team project virtually. Now I'll pass it on to Craig for the acknowledgements.
Thank you, Kaylee. So for our references, we have a list of documents that we have used while working on this project, including the datasheets for our components, the TNC 3.2 microcontroller board, and the FTC 1004 chip. So finally, we would like to acknowledge everyone that helped us along the way. We'd like to thank our team of sponsors at Roche Tissue Diagnostics, including Daniel O'Connor, Stephen Lay, Nima Jamalpour, and Matt Met, for supporting our team and providing valuable feedback throughout the project. We'd also like to thank our mentor, Pat Caldwell, for guiding the team through the process. We'd also like to give a special thanks to last year's team for their generosity with their information and the University of Arizona Engineering Department, especially Gary Redford, Claude Merrill, and Don Newman, for giving us the necessary resources to complete our project. Finally, for everyone on Team 21019, thank you for watching our video.